Hi, everyone. It's Will. Welcome to the fourth Hangout in the Intro miniKanren series. So last week we had a little bit of internet trouble, so hopefully this time it won't be. We won't have any issues with that. I just got back from New York. Had a lot of fun. Gave two talks, one at Lisp NYC and another at Papers We Love. Both of those I talked a little bit about miniKanren, or at least showed off Barliman. And in the Papers We Love talk, I actually walked through how to write a scheme interpreter, which is one of the topics that we're talking about in the series. And I define the scheme interpreter in a little bit of a different way than we're going to see for our first scheme interpreter, but I tried to keep it all compressed. So in maybe an hour or 15 minutes or so, I started from this is 5, a scheme program 5, and got all the way up to a scheme interpreter that could run in scheme. So it's very compressed, and so it's probably not a great introduction if you don't know anything about functional programming or Lisp or things like that. But it tried to cover all the core ideas. So that might be something that people are interested in. I'll post a link when that goes online, hopefully, that talk. It's sort of a different form of exposition for some similar material. It's very compressed. All right. Well, we've got pretty much a full house today. 1, 2, 3, 4, 5, 6, 7. Wow, that's good. Welcome, everyone. And we are going to talk about environments today and start writing real interpreters. So that's good. I'm excited. We talked about pattern matching. Last time we talked about lexical scope and shadowing of variables. Now we're ready to start talking about environments and environment lookup and some real detail. And as soon as we do that, since we know pattern matching, we know lambda, we know all that stuff, we can just get into writing interpreters. That's great. So we'll write something today. Let's get started. So let me do my screen sharing and bring up my Emacs. All right. Intro 4. Yay. Okay, so it worked. All right. So if you remember last time, we were talking about, between internet outages, we were talking about free and bound variables, and we had things like let x be +2, 3, and let y be times x, and then maybe here we say let x be 7. Now we're going to add x and y. So here's just a little scheme program. So we're using these lets. And remember that let corresponds to a lambda expression and a direct application of that lambda expression, procedure application of the value back the procedure from that lambda expression. So if we try to play computer, basically, and we're working from the outside in, we say, all right, we're going to create a let binding for x. X is going to be bound to the value of this expression +2, 3. So that means inside the body of the let, which is the scope of x, x will be bound to 5. Okay, x is 5 there. And now, when we're trying to find out the value bound to y, we're going to multiply x by itself. So we look up x in the current environment. The current binding of x is bound to 5. Okay, so we're going to multiply 5 by 5, and it's going to give us 25. So therefore, now we have y is 25. And at this point, x being 5 is still in scope. And now we can go down to the next expression. Now, x being 7. Well, that's pretty simple. X is 7. Now, notice we have 2 x's, 2 bindings for x. But that's okay because they have different scope. The body for the scope for this x is the body of its let expression. Okay, the scope for this x is the body of its let expression, which is inside the body of the outermost let expression with the x. And in this x is going to shadow within its body the value of the outer x. So if we try to add x plus y inside the body of the innermost let, the x value here will be bound, or the x variable will be bound to 7, and we won't see the 5. That x bound to 7 shadows the binding of x to 5. So this x will be 7, and y will be 25. Okay, so we have this notion of scope, notion of shadowing. If I were to do something like add x to the value we get back from that let expression, and in this case, this x out here is going to have the value 5. So we're adding 5, or I can actually swap these two if I want to. That's probably more interesting. So this x here actually has the value 5 because it's not within the scope of this innermost let. So so the x binding is associated to the x up here. The x binding is for the x5. This, when you have this variable reference, you look up x is 5. So it's not like by let binding x to 7, we somehow change all x's in the program to have the value 7. We're not mutating or destroying those values. It's just that within the body of that innermost let, x is 7. Outside the body of that innermost let, if you're still inside this outermost let binding, then x is going to be 5. And if you're outside this let binding, the x being bound to 5 doesn't hold. So if you had an x outside the let, that may not be bound at all. All right. So in this case, let's just figure out what the value of the expression should be. So here we're adding x plus y. So that's 7 plus 25. So that's what, 32. And then this x here is going to be 5. 32 plus 5 is 37. Let's see if I think it's 37. Yeah, there we go. So we got the right answer. So we have these two references to x that have different values because they're within different scopes. Okay. And what we started getting to last time was I started showing a representation of these environments that looks a little differently. It looks a little different. A representation of these bindings. Go back to our sort of simpler example. And what I started talking about are these environments. So here we're talking about variables being free or bound. Here x is bound within the scope of the let expression, the body of the let expression. But we can also talk about environments. And we can say that, initially, our environment may start out empty. So we could represent it as a list of bindings. Now, it depends on your point of view because, really in Scheme, if we have all of Scheme, there's a binding, there's an environment that starts out with lots of bindings in it. We have a binding for plus, we have a binding for cons and car and for let and for lambda. All those things are already bound. But if we're thinking only in terms of the variables we're introducing, then we could talk about, well, we have this empty environment, or at least an initial environment. We have whatever environment we start with, and we're going to extend that initial environment. But a lot of times we'll just kind of say the environment's empty. What we might really mean is that we have an initial environment that we might want to extend. Okay, so let's keep track of the environment. Initially, we're going to start out with an empty environment. Now, we know that within the scope of this x, within the body of the let expression, x will be bound to 5. So now, have an environment where x is bound to 5. So if we look at it, our environment is a list of pairs, and we have a some representation of a variable, and then the value bound to that variable. Okay, so we have one binding in this environment. We have another extension to this environment. We could say y is 25. It's still in place. And so we take that old environment, and then we're going to extend it. So we can think of it as we're consing on a new pair if we use this representation of environments to the old environment. So if we want to extend x with a binding of 7, we're going to end up with x dot 7. And you think of it, we just cons on this pair, shows a binding between x to 7 with this existing environment. And this is an interesting environment because there are 2 occurrences of x. And you can see how the shadowing works. If we were to look up x, the binding of x within this environment, by just going through the list left to right, just sort of what we'd call cootering down the list. We're taking the cooters as we go. Then the first x we come to will be the x bound to 7. And then we stop because we found a binding for x. So by doing this, by having this representation of an environment where we're consing the new bindings onto the front, we handle shadowing automatically because we'll just never get to the x being bound to 5 if there's an x bound to 7 in the front. Okay, so this is what we call an association list representation of an environment. So association list representation. There are lots of, and this is also called an A list. And so we have the empty association list and association list with one association and so forth. And so an association list is just a list of pairs. That's all it is, where we have something on the left of each pair, which we can think of the key that we're looking up, and then something on the right, which is like the value that we're going to get back when we look up the key. That's it. So we look up x, we get back 5. We look up x here, we get back 7. We look up y in this association list, we get back 25. So we're going to represent our environments as association lists. There are lots of other ways we could represent environments. We could represent environments as procedures. We could represent environments as tagged lists. I'll just show you briefly what a tag list environment might look like. So we could say the empty environment, something like that. And then, I'll call it empty env, just to be a little short. We have a list containing the symbol empty env. And if I want to extend the environment with an association between x and 5, then I would have the x, I would have the 5, and I'd have the old environment. And I can keep adding on to the structure. So I'll build another list, another xenv on the outside, building up these lists a little bit at a time, where y is bound to 25, x is bound to 5, and then that last environment, where x is bound to 7, where we're shadowing the x, would look like this. And this representation of an environment works really well with pattern matching. With our p-match, we could p-match against these lists and p-match against the xenv symbol versus the empty env symbol, and p-match against the variable and the value and the old environment and all those sorts of things. Maybe we'll end up doing that. But the point I'm trying to make is that there's more than one way to represent the environment. The environment is really an idea or an abstraction. An environment is some platonic idea of association between variables and their values. And when we're implementing an environment as a programmer, we have to decide which representation we want. There are many choices, and they have different trade-offs. So this is a tagged list representation. And we might go ahead and implement both versions today. so you can kind of see how they differ. All right, so that's the association list version, and then this is the tag list version. But you can see both data structures represent the same information. That we have association between x and 5 and y and 25, and then x and 7. Okay. All right. So this environment is going to turn out to be, a key data structure that we're going to use when writing interpreters. This is we're going to be writing what's called an environment passing interpreter, and we'll be passing this data structure through so we can look up values for our variables. We can get the value of a variable. If we don't have variables, then we're reduced to some sort of simple calculator type interpreter, which is fine. But the interesting things happen when we have variables and lambda and procedure application, all those things, and those operations are all intimately connected with the notion of an environment or variable binding. All right. So now that we have some notion of what an environment is and different ways we might represent that, now let's go ahead and write a little function that will look up a variable in the environment and tell us what it's bound to. And we're going to call this lookup. So we're going to define a function called lookup. And because we're going to look up some variable x in an environment. And here we can make a choice. We could use pmatch, or we could use con, we could use if, or whatever. For this version with association list, I'll use cond. All right, so we're going to have some clauses. And if I go back and look at sort of these examples for the association list, that will hopefully help me write my code. So if I look at it, I can see that I can start off with an empty environment. An empty environment is the empty list in this representation, the association list representation. And the empty environment is not going to contain any bindings at all. So I can check to see if I have the empty environment by asking null question mark. Is the environment empty or null? If so, what do you think should happen? What should I do if the environment is empty? Any ideas? Going to make you do some work. Any thoughts? Yes, return null, x is null, return none. Well, we have to decide what we want to do, right? Sorry, Python. Okay. Well, we could say, well, we look up something in the empty environment, we get back null or something like that. Well, what happens if you look up an environment? Yeah, not a number. we could go PHP or something. What happens if, in Scheme, we try looking up a variable that's not bound, like let's look up x. Exception, variable x is not bound. We're basically getting an error or an exception or whatever, right? So we want to do something other than just return null. We actually want to say, oh, that didn't work. We're going to fail. No, I shouldn't say fail. Fail's logic programming. We are going to error out. Okay. So I am going to make a call to error. Error takes the name of the function or whatever is producing the error, and it can take a string. That actually error has a somewhat complicated interface, but I'm going to use this sort of simple version of it, and we'll just say unbound variable. So if the environment's empty, we know x does not occur, the variable x does not occur in that environment. So therefore, that's an environment lookup error. That'd be exactly the same as if we typed something at the scheme REPL for a variable that's not bound. We're going to get some error message saying it's unbound. Great. All right. And in fact, now we can take. So we have a working version of lookup. Doesn't work for all our tests, but it works for some. I can load this thing. And let's test it. So we can do lookup we know that our environment is going to be empty, the empty list, and we're going to represent our variables as symbols, scheme symbols. So I'm going to look up the variable y in the empty environment. Now let's see what happens. You can see when I evaluate that, basically I'm typing in like an Emacs command to evaluate it. Let me just show you explicitly. I can type it in. Okay, when I do this, I get an error message or exception. Exception in lookup. So we can see we're actually getting the right name of the function. That's our error message. Unbound variable. So you can see the string that we've included is showing up in the error message. Now, this isn't a perfect error message because we don't know which variable is not bound. So if we want to, we can add a little more structure to the message. And one way you can do that, this is, maybe a little more advanced schemely stuff. If you're familiar with languages that have string formatting and string interpolation, all this stuff, maybe you'll be familiar with this. But the bottom line is we can have this call to format, which takes a string and it takes takes some arguments, like some expressions like x, which is the symbol bound to the variable, representing the variable. And inside the string, we can put this tilde-s thing, and that is scheme speak for saying, or at least Shea scheme speak for saying, okay, wherever you see the tilde-s, substitute into the string the value of this corresponding argument to format. Okay, so if x happened to be list ABC, then we'd see unbound variable in the list ABC. If x happened to be 5, you'd see unbound variable 5. If x happens to be the symbol s, or you would see unbound variable tilde-s, or if x is y, we'll see unbound variable y. So hopefully we'll see unbound variable y. Yep, sure enough, unbound variable y. Okay, so if you don't really want to mess with the vagaries of format and error, you don't really have to worry about it. The other thing you could do is say you didn't know how error worked and you didn't know how it worked and all that. The most important thing really is just to stop the program from executing and giving you nonsense value. The other way you could create an error would be, to do something like call car on 5 or something stupid like that. Now the error message you get will not be very nice. Exception in car, 5 is not a pair, right? You'll get some stupid error message, but it will stop the evaluation. So there are things you can do like that. Or you could say car of, quote, unbound variable. This is really bad hack. But you can do that, and it'll say exception in car, unbound variable is not a pair. So there's your error message. I don't recommend doing this, but in a pinch, if you're stuck in some system and you don't know how the errors work, you can do little hacks like that. And just call some function that will error out, because you can only call car on pairs, and you can kind of jury rig an answer there. Anyway, we'll do the nice interface. Whoops. So you see, oops. A reasonable error message, fine. And the error case now works. Okay. Now we are going to want to see what happens if we have a non-empty environment. So here's an environment, just so that we can look at an example. So another environment might look something like this. And in this case, we have an environment that has, multiple bindings. It's not empty anymore. So when we have a binding, well, a binding is an association as a cons pair, where we have some symbol representing a variable, and then, as the car, and then the coder is the value bound to it. So we could do some sort of check to see if the car, so we have to be a little careful. what is the car of x? Well, the car of x is not y, because the way the association list works, it's a list of pairs. So the car of this association, car of it is actually the pair y.25. That's the car of it. So what we actually have to do is take the car of x to get the of the environment. The car of the environment is going to be that variable, like y. And we want to see if that variable or symbol representing a variable is the same as x, the variable we're looking for. So if those are the same, then we found the pair. We found the association. And so now we would want to return 25 in this case. So once again, the car of the environment is going to be the association, y.25, that pair, const pair. And then the cdr of that pair, the thing after the dot, is going to be the 25. So what we have to do is return the cdr of the car of the environment in that case. So once again, we can try our lookup. We don't, the general principle, we don't have to finish defining the entire code before we actually run it. So let's try it. Bound variable y. Oh yeah. Well, I want to comment. So let me try doing a lookup on this environment. Lookup in that environment. I should get back 25. Try that. And I do. Okay. And I got to try looking up x. Oh, that didn't seem right. Well, what's going on? Well, the reason it didn't work is the first thing in the association list isn't a binding for x, it's a binding for y. So we have to do a recursion to get to the x binding. So we left out a case. So the case where we haven't found the binding right away, we need to keep looking through the environment. And how do we do that? Easy, we just recur. Look up x on the rest of the environment. We already looked at the car in the environment. It's not that association, so we look in the cdr of the environment. Have the recursion. All right. And once we have that, let's see. Yep, sure enough, it works. And we could try looking up z in that environment, or z. And now we get the right answer, which is an error, unbound variable z, or z, okay, because z isn't in there. So it looks like we're handling our recursion correctly. Now, one thing I'll point out is our notion of equal here is a little bit of an overkill, because what we were looking at are symbols, like quote y, quote z, or whatever these quote expressions evaluate the symbols. And it turns out in Scheme, we don't need to use EQUAL to compare them. There are other notions of equal in Scheme. One is called EQ ? Which you can use for pointers. Another, which Dan likes to use, is EQV. So the calling EQ is pretty standard. And exactly how the different notions of equality differ is a little bit subtle. Actually, Scheme has many notions of equality. I'll just show you one quick difference between equal and EQ, for example. For equal, if I say it's x equal to y, it's going to say no. And same thing with EQ. If I have numbers, how that works is 5 equal to 5. It's 5 EQ to 5. is some really big number equal to itself? It is. Is it EQ to? It is not EQ to itself. Oh, that's interesting. Okay. What about a list? Equal the list ABC, list ABC. So those are equal. Are they EQ? No, they are not. So EQ you can think of as what is called pointer equality. Basically, is this the same object in memory? And that's why these really long numbers are not EQ. They're equal, but not EQ. They have the same value from an arithmetic standpoint, and they print out the same. But with these really large numbers, Scheme has to, Shea Scheme can't represent those within a single word of memory, actually. So they're not considered pointer equal. So anyway, there's some subtle differences in notions of equality. But what I will say is that symbols in Scheme are designed to be able to be compared with EQ. And so if you use EQ, in this case, we're just comparing symbols, that is safe. Okay, so if you look at Scheme code, you would also often see an EQ question mark in this code instead of an equal. And one reason is that equal question mark can be a more expensive operator because it has to deal with lists and arbitrarily large numbers and things like that. So if you're looking at Scheme code, you would often see for comparison of symbols, EQ question mark. Sometimes you'll see EQV, which is in between EQ and equal in terms of its behavior. And if you really want to know the exact semantics of EQ versus EQV versus equal, you should look on the Scheme standard, or you should look in Kent's, the Scheme programming language, 4th edition, and they'll give you very detailed explanation of the differences. But they are quite subtle differences, and equality in Scheme, there's also another notion of equality on numbers. So we can also do the equal sign. Arbitrary precision numbers. So, EQ, EQV, equal, and then the equal sign, numeric equal sign. Those are 4 notions of equality in Scheme. There are many others. Point is, it may be more idiomatic to use EQ here or EQV. The other thing I'll point out is this car of env is kind of annoying, and this cdr of car of env is kind of annoying. It's a little hard to read. It's kind of long. So in Scheme, what people are much more likely to do is they would probably write this as the cadr, or sorry, this would be the car r, the car of the car. They would just write that as car r, two A's. That's the same as chaining a call to car and then another call to car. So that would be the car r. And then the cdr of the car is the cadar, the CDAR. Okay, and the way you can chain these cars and cdrs together just by stringing together A's and D's inside, in between the A's and the R's, that really is the reason that a lot of Lisp programmers and the reason Scheme has kept car and cdr, even though car and cdr are sort of historical names, having to do with specific hardware that Lisp ran on originally. This ability to chain cars and cdrs makes it easy, and makes it a little more readable, I guess. But the other thing, we can also define it in another way. So let me get my tests here. So I can do this, bam, bam, bam. Great. This definition works. But another way we could define lookup is to actually try to match the structure of the list a little more closely. So I could define lookup, use pmatch instead. I'm going to pattern match on the environment. And if I do that, then the empty environment just looks like the empty list. And now I have, I could also have something like this, where I have y dot v for value, and then here's the rest of and that could be a pattern. And so I can actually write down a pattern that looks like the association list. If I grab, association list like this, you can see that that the structure looks similar. That this pair y.25, or maybe I call it z.25, z.25 looks similar to this y.v. And if we remember our pattern matching, our p match, this comma y will become bound with, or pattern match against, the symbol z, and this comma v will become bound or pattern match against 25. And then here, this dot comma env hat, or old env, or whatever you want to call it, you can call it any name you want, the thing after the dot will be associated with the rest of the list. Because if we remember, going back to our conses and our pairs, that association list up here is actually the same, writing it this way. Have a dot and then wrap a pair of parens around the rest of the list. Okay, and then this itself is an association list. So the cdr of the entire association list is an association list. So this is a way of doing physical pattern matching, or sorry, I shouldn't say physical pattern matching. It's a way of doing pattern matching against an environment written as an association list, where the pair structure becomes evident. So the dot comma old env is going to match the rest of the environment. And now I can do something like have a little test. I can say if eq y to x, then return v, otherwise return lookup of x in the old environment, or the rest of the environment. Maybe I call it rest in the rest of the environment. I call it old because we're consing onto the environment, so that environment was there first. Okay, so now I can write lookup that way using the pattern matching against the association lists. And now the pattern looks very similar to the structure of the association list itself. So I don't have to think about taking cars and cdrs and all that sort of thing. And as the structures of my lists become more and more complicated, the attraction of doing this pattern matching becomes greater. Like it just becomes much simpler to do pattern matching than to try to take cars and cdrs, or at least it becomes much more readable. So if I try it, still works. Still works the same way. Okay. And we can do one more version. Let's go back to this version with the tag lists. That way. List representation. And I'm going to take version for association lists and do something similar. So I'm just going to change these patterns. So used to be with association lists, the empty list represented the empty environment. Well, now with the tag list containing the symbol empty env is now the empty environment. So just replace the pattern. And now it used to be this association list structure was representing an extended environment, basically. Now, instead, we're going to have this tag list. Okay, second, so I can rename things. Okay, so it's going to have the tag extend. It's going to have a variable here, y. It's going to have a value here, v. And then it's going to have the old environment. All I had to do was change the patterns. I didn't have to change any of the rest of the code of lookup. And now it works on this now our code works on these other environments. So I'll show that. Here's a test with lookup. Let's look up y in this extended environment. Y is down to 25. So let's see. Oh no, come on, Emacs. You can do it. You can do it, buddy. You can do it. All right. Emacs can't handle it, so I will have to restart it. Sorry. Okay, so there's a perfect opportunity for questions as I restart Emacs. Any questions about that so far? All right, Emacs is back up. Match. Load the whole file at the second. Here's my version of lookup that works on tag lists, and we'll see if I can actually look something up. Yep. Fair enough. Y gives me back 25. And if I were to look up X, we'll see the shadowing work. I get back 7 instead of 25. And if I look up Z or Z, then I get the error. Okay. So you can see that I can write lookup many different ways. I can use pattern matching. I can use cond using car and cdr. I can use different representations of environments. It doesn't really matter. Conceptually, it's all the same operation. We just abstractly, we are looking up some representation of a variable in some platonic notion of an environment that's binding variables to values and finding the value. That's all there is to it. Okay, so it doesn't really matter how we implement it. You could implement this in any language of your choice. There's nothing here that has anything to do with scheme. The only part that's a little schemely is that we have symbols, and some languages don't have symbols. But you could represent variables other ways. If you're in C, you could have some sort of structure representing variables, and maybe numbers or something like that. It's maybe not as abstract, but you could do it. You could have strings representing variables instead, that kind of thing. Right? Okay, yeah, a lot of languages will use strings to do it, to represent variables. But in any case, we now have different ways of representing environments, different ways of looking up the values in the environment. And that's one of the key operators in an interpreter is environment lookup. Okay, so we've got a good handle on that. We can do it one of many ways. Now I'm going to come back up here, and I'm going to add this thing called hashbang EUF. What that does is it tells ShayScheme to ignore everything below the hashbang EUF in the file. And the reason I'm doing this is that I've got all these definitions of lookup right now and all these kind of tests I just threw in, and some of which are supposed to make the loading or the evaluator, the REPL fail or give an error. So I don't really want that code to run when I load the file. So I'm just kind of putting it in there for posterity, but we'll kind of clean up our implementation in a minute. Question here, Daniel. Why do the more complex tag representation versus the association list? Okay, that's a good question. So, why use this representation instead of association list? Well, they're all different trade-offs, right? In some sense, this representation is somewhat documenting. If say instead of having one data structure, I had 20 data structures, and they were different forms. Or actually, this comes up all the time in interpreters. You might have both environments and what are called stores. Or in logic programming, you have something called a substitution, which looks like an environment. And you can represent all these things as association lists. So if I gave you some complicated implementation of some program and you didn't know all the details, and you see that there are 3 association lists being used all over the place, it'd be very easy potentially to confuse those or have difficulty telling what's going on. Whereas here, you can just immediately tell, hey, this is an extended environment. It's very easy to tell. In fact, using procedures to represent environments are sort of the worst from that standpoint, because all you get back is procedure, and all you can do is call it. You can't actually look inside of the procedure. So this is a little more verbose, maybe a little more documenting. It also just shows that our representation doesn't matter. We could be using records or structures or vectors or all sorts of things, hash tables. There are lots of data structures we could use. Just showing that with lists, there are a couple of ways we could do it. Actually, we could tag it any way we want. And I guess the key idea here isn't that you might want to use the tagged list versus the association list. The key idea here is that any representation we pick is an implementation choice. It's an implementation decision, which is separate from the ideal, abstract, Platonic, mathematical, logical notion of an environment. Okay, so what I don't want you to think is that an association list and environment are the same thing. An association list is one way to implement an environment. A tagged list is one way to implement an environment. But an environment, in some sense, is this mathematical notion, right? So that's the reason I'm trying to show you different implementations of an environment, is to try to drive that fact home. It's less important that you're using a tagged list. Okay. And yeah, so just by showing it a few different ways, that hopefully makes it clear that the lookup function is not inherently we're writing an implementation of lookup, and there's some mathematical or conceptual notion of a binding between a variable and a value, but our lookup function is not that mathematical notion. It's an implementation level set of decisions we've made. Many ways to implement lookup, many ways to represent environments. Okay, just remember that one of these concepts is this abstract mathematical, beautiful Platonic notion, and then there's the scheme code. And we really shouldn't confuse the two, because we can't just implement the math. We're trying to run something on a computer and move electrons around, and there's some sort of Platonic notion that we'll never be able to completely capture. We can only capture aspects of it in our implementation. Okay. So we've got a good handle on environments. We can look up a variable in an environment any way we want. Now it's time to go ahead and write an interpreter or evaluator. And so we are going to write a function called eval. Well, some version of eval. I will call this eval exper for eval expression. This is sort of the standard name I like. And it's going to be a procedure. I'm going to take some arguments. I'm going to take an expression. So let's just start with that. Let's just start with the expression and see where we can go before we might need another argument. Now, we have to decide what we want our language to be able to interpret. And we can start out doing some calculator related things. That's kind of simple. So one of the things we might want to interpret is like 5. Okay, like the number 5, and that should evaluate to 5. So we evaluate just numbers themselves. All right. So I'm going to write the interpreter using pmatch, and we're going to match against the expression. And I'll use this the square parens. Remember, these are the same as round parens, but they're as long as they're matched, but maybe a little easier to read the patterns. Basically, I'm going to write a little pattern comma n. If you remember p match, comma n matches against any expression, anything here. So we're going to have to use a little guard, calling this number predicate, to make sure that the match really only works against numbers. 5. The predicate inside of the guard, what's called a fender technically, is considered part of this match. So both the pattern and the guard, the pattern has a match, the guard has to return a non-false value for this entire sort of pattern match to happen, and then we're going to return whatever value we have on this right-hand side expression or below the pattern. So in this case, if we have a number, we're just going to return it. The number just evaluates to itself. So that's a pretty simple interpreter. Let's see if we can try that out. Load. Actually, let me. And I can call eval expr on 5, and I get back 5. Sure enough, that works. Now the problem is, or I shouldn't say there's a problem, but we do have to be careful. So this eval expr 5 thing is not really what we want. We do have to be careful. And the reason is when we are trying our evaluator inside of scheme, remember we're writing this eval expr as a scheme procedure, a scheme function. We're running it inside of scheme, okay? And because this is a procedure, scheme is going to evaluate whatever expression we give to it. This expression that's passed to eval expr will be evaluated in scheme. So for example, if I did, wrote down 3 times 4, I have not added multiplication to eval expr. However, it may appear that that multiplication works properly because I get back 12. I have not added lambda or application, but if I write lambda xx applied to 5, I'll get back 5, and it looks like, wow, somehow lambda is working, multiplication is working, procedures application is working. The reason these appear to be working is that these expressions, the application and the lambda and this multiplication, are being evaluated just in scheme. Just like if I type 3, 4, multiply 3, 4, and that value of 12 is being passed to eval expr. Okay, so what we want to make sure is that whatever expression we're interested in evaluating doesn't get evaluated prematurely by scheme. And we can do that by using our friend quote. So we're going to quote whatever expression gets passed into eval expr. And now you'll see that it doesn't work anymore. Eval expr isn't handling multiplication yet. So we passed in the list times 3, 4. Eval expr doesn't know how to handle that because it only knows how to handle numbers. So we are going to get in the habit of always putting a quote in front of any expression we want to evaluate. And that includes things like 5, which are what are called self-evaluating or literals. So 5 just evaluates to 5. We're always going to put a quote in front of any expression, including 5, even though it doesn't really need it, just to keep ourselves honest and make sure that we're never going to accidentally evaluate something in scheme. So the real test is, to see if the numbers are working is to put a mark in front of it. Okay, so that's our simplest test. Evaluate quote 5, we should get back 5. Okay, and that works. Once again, we have this idea of trying to, build up our expressions a little bit at a time, build up our interpreter a little bit at a time, our definitions a little bit at a time, and testing it as we go. So we have numbers. All right. Well, maybe we want to be able to do something like add 1 to a number. So add 1 in scheme will add 1 to whatever the value of that expression is. So let's try adding 1. So this is why we're using pmatch, is so that we can match against expressions like add1. And now how are we going to add one to a number? Well, here's the magic of the type of interpreter we're writing. We're writing a scheme interpreter in scheme. Scheme already has add1. So we can use add1 from scheme. So we can just call add1 of scheme on whatever the value of E is. Okay, we're just calling schemes add1 here. How do you know what the value of E is? Well, you have to evaluate it using eval_expr. We're going to make a recursive call to eval_expr and pass in E. This may look a little strange. So remember, in pmatch, there's an implicit backquote or quasi-quote in each of these patterns. So that's what it looks like. And if you were to use racket pattern matcher, you have to write the backquote explicitly if you're going to do this sort of thing. The racket pattern matcher uses somewhat different syntax, so you have to look that up. But in racket, it requires you write the backquote explicitly. So there is a backquote here. So this is like a list we're pattern matching against. And then this is a procedure called the schemes add1. So, it might look a little strange, but it's sort of on purpose. We want, the add1 list that we're pattern matching against, that expression, to sort of just turn into a call to schemes build in add1. We're going to leverage the existing scheme code to be able to do this work. Great, so let's try that. I evaluate this expression. Now I can go to my call to eval_expr, make sure to quote my expression. I get back 6. And here's a critical thing. Whenever you're testing these programs, if you have something like add1 that takes an expression as an argument, don't just test it with things like 5 that evaluate themselves. You want to test them in a nested fashion where you have multiple calls to add1 chained together. And sure enough, that works. Sometimes people will just forget the recursive call and they'll do something, they'll just say E there. Okay, and if you do that, it might appear to work because add1 of 5 gives you 6. But as soon as you try doing nested calls, you'll see it doesn't work because add1 of 5 is not a number. So this is one way to test to make sure you're not forgetting your recursive calls, is to make sure your tests include nested sub-expressions using that operator. For that, sure enough, it works. Okay, so now we're getting to the point where we're starting to get some tests going. And I've been a little sloppy with my testing technology. I've just been kind of doing this by hand, typing it into the REPL, trying to save the answers and things like that. But as we start getting more and more of our tests for the interpreter, we're going to want to actually have a little bit of help or a little bit of infrastructure for running these tests and making sure that we're getting the expected value back. So we don't have to run by hand a bunch of these expressions and by hand compare them with the expected value. So we're going to go ahead and add a little bit of a test macro. I think there may be a question first. Okay, yeah. Yep, what is the idiomatic testing framework for Shea scheme? I don't know if there is one. There is some idiomatic testing stuff for Racket. There's like this rack unit, things like that. What we're going to use is kind of a budget tester, but it's like a little macro, I mean, what a surprise. pmatch is a macro, or tester is a macro. So it's very easy to write these macros in Scheme to do testing. And so we're going to just have a little syntax rules macro. In fact, maybe we should just write it. That might give us some insight. So let's go ahead and write a macro. See if I can pull this off. Define syntax. Let's call it test. And we are going to have, I'm using these square brackets again, just so, they're the same as the rounds, but it just, when you're doing pattern matchy things, it can make it a little easier to see the pattern. So our macro is going to be called test. And We can have a name for the test. And then we're going to have an expression and the expected value. That's what a macro is going to look like, our test macro. And so I have something in mind, we'll call it test 1 or valexpr test or whatever I don't know. Come up with some naming. And then the test will be, a call to a valexpr. We could do like a valexpr 5 or a valexpr num or something like that. We're going to evaluate a number. And then the output that we expect is 5. Or, we could do add 1. Add 1 of add 1 5. So we're going to testing our add 1. And we expect to get 7 back. Okay, so that's what a test might look like in our very, very simple testing technology. And so what we're going to do is going to expand that to some code, which is say let bind v to whatever we get, and we evaluate the expression. And then we're going to do a test if equal v to expected value. Then, I don't know. Well, actually, one way to do it, we could return some message if it worked, but probably the more reasonable thing is like, to do something special if it doesn't work. So, we can just return yay or something like that. And if it doesn't work, we could say pass test or something like that. If we really want to be fancy about it, we could say format test. Actually, we could just display that. And then have another display and the test name. Like that. And then you can call it new line, which will print out new line. And then because if the consequent part of an if, or the part that gets run if this true, if the test is true, can only have one expression, we have to wrap this in a begin. So this is one of many, many ways we could use to print out the output. The display is sort of this low-level scheme interface for just printing out a value. So if the test passes, we say pass this test. And if it doesn't pass, this is the more interesting case. In this case, we could print out a message. We could signal an error. We could write to some global variable telling how many tests have failed. We could do all sorts of things. Let's just fail fast. So if in this case, there's just going to be an error, like something, it really didn't work. Let's see if I can get this part. Name of the error. And I want to have some error message. Failed. And maybe I'll put like some stars or something just so it stands out. And actually I can say like test blank failed. User friend format. I'm just trying to show you a few different ways you can do strings and formatting and stuff like that in Scheme. Remember, we got this tilde-s thing, which gets replaced with the value of this argument to format. We can have as many arguments to format as we want after the string. We can have as many tilde-s's as we want. They just have to line up. We have to have as many tilde-s's as we have arguments. And so we can say, oh yeah, so test name failed. And then we can say something like expected line here so we can read it. Expected some value dot. Now I can say Okay, so I have 3 tilde s's, the name of the test, the value that was expected, and then the value is returned. So I can put an expected val, and I can put in a v, which is the value that was actually produced. So this is a little simple test macro, and hopefully this actually works. May have gotten something wrong, just like I managed to fumble the quasi quote last time. So let's see if this actually works. Okay. Oh, at least try that. Expected. Oh, I think I called it expected values somewhere. So names again. All right. So I passed that test. And there's actually something besides display. Let's see, what is it? There's D and there's S. So what's the thing besides display? I forget in Scheme. It's been so long. I always do like format or printf. There's display and there's oh, it's write. Yeah, okay. I can write the name if I actually want to see a slightly different output. I'll write the name. And now you see it's got the string wrapped around it, which might be nice for having complicated names with parts. Okay, so I can use write instead of display. And then, well, now we need to test something that failed. So maybe, maybe we say we get 8 instead of 5. What does it do now? So we got an exception. Great. Actually, I guess we don't need the dot of the. If we're just going to fail with an example, or if we're going to stop the interpreter with or a compiler with an exception, the REPL with an exception, we don't really need the asterisks. Test eval expr add 1 failed. Expected 8, but got 7. Oh, all right. So I'll just get rid of these asterisks. Try it again. Okay. And one more thing I can put in here. I think this will work. Yeah, so now you can see my error message. It's a little easier to read because of the new line. So maybe I'll put in one more new line. This is kind of a good example of the sort of process you go through when developing something like a little test macro or any sort of little macro or function like a little helper. We're gonna kind of build it up piece by piece. Okay, so now we have a test macro, and this is something we can use now for testing. And so at this point, I can replace these sort of handwritten tests with calls to my test macro. So I can say test, this is val expr num, just have a constant number. And evaluate to 5. So now I've got these tests, great. And let's try loading. Maybe I'll just back and load that whole file. Okay. Now I'm starting to cook with gas. I'm starting to have a real test macro, and it's passing those tests. Okay, so I've got, that's great. Now if I wanted to add another test, I might want to add like a big num test. The big num is an arbitrary precision number, so I could do Load it. It's test pass now. Great. So this makes it a lot easier to do testing, and also shows you sort of how you might use a macro to give you similar behavior. So we've got a little bit of a calculator now. It's it's a pretty simple calculator. We can have a constant number, and then we can add 1 to that number. That's all we can do. So let's try, just adding one more operator. Let's do something like multiplication. So with multiplication, we have 2 sub-expressions, multiply E1 by E2. We're going to play exactly the same game. We're going to multiply the value of a val expr E1 by the val E2. Okay. And now I can go ahead and add another test. I can add a times test. Say multiply 3 by 4. Yeah, that's test number 1. This is where you have to start thinking more engineering-y, or how do you want to have naming conventions and so forth. But in any case, I do want to make sure that so 3 times 4 is going to be 12. 3 times 4 is 12 times 5 is 60. Wow, this is a lot of work. So let me try this version as well. Multiplication should be commutative. Okay, so now I'm trying all the sub-expressions just to make sure I got my recursion right. Okay, try running that. Okay, all the tests pass. Great. So now I can start making more rapid progress. I can start adding all sorts of operators. I'll just add a couple very quickly. I'm going to add sub1 as well. This is the only operator. Sub1, and I'll number one more, which is a 0 question mark. And so you can see I can sort of copy and paste 0 question mark. They all have sort of the same structure, right? I'm just calling the scheme equivalent. And I should point out that say I was using some version of Lisp or Scheme or whatever language that for whatever reason didn't support add1. Well, in this case, I could just use plus and 1. Doesn't matter. I'm still using Scheme's built-in functionality. It doesn't have to be exactly 1-to-1 in terms of the primitive I'm using, as long as it has the same behavior. Okay, so I have 0 question mark. So let's just add a test for that, and I have add1 and sub1 now. So let me add a sub1 test. Sub1 test is like add1, except it goes the other way. Sub1 of 5, 3, and we have 0. Okay, so 0 question mark of 0 should return true. Now here I'm going to have a few versions of this, so I'll give it, kind of number it. And 0 of 1 is going to be false. And I want to have another test. I got to make sure that that I'm testing my recursion. So 0 of add1 of 0, that should also be false. And I could be careful here. 0 of sub1 of 1 should be true. Just added a bunch of tests, see if those work. Those all pass. Great. All right. So we've got plenty of arithmetic operations for a simple, boring calculator. And now we're going to start adding some things that are a little more interesting. So the next thing we're going to add is if. We're going to add if. So if, and of course, let's just make a choice. if as a test, for sort of the formal names for those, or I could do if E1, E2, E3, it doesn't matter. I don't care. But these are sort of the names that I normally think about. I don't know. We can do E1, E2, E3 also. Just remember that E1 is the test part. So in this case, we're once again going to use schemes if. Right? We're just translating these things into the underlying scheme. So we're going to evaluate E1. And if E1 is true, then we evaluate E2. If otherwise, we evaluate E3. That's it. So now we have if. And it's the same pattern over and over again. We'll see in a minute the pattern is going to get a little more complicated when we go to. But right now, we're still in sort of that. All right. So let's have a call to if 0 of 0, which would be true, then return 5, otherwise return 6. Okay, so that should return 5. Another test. This is how you test an interpreter. Start building it up like this. If 0 of 1, which is false, return 6. So we got some very simple tests here. And of course, we want to make sure that we're handling our recursions properly. We can have more complicated sub-expressions. So, start doing something more interesting. Sub1 of 6. We can do these sorts of expressions. So that's going to be sub1 of 6, which is 5. And so forth. We can go as far as we want. We can also start nesting if expressions as well. So we can have an if with an if and so forth. I'm not going to get into that business right now, but you can see all the tests are working so far. Pretty simple. And so far, you notice that we just have been able to get along with passing along the expression. We haven't had to do anything else. Right. We're now at the point where we can add something a little more interesting. And the thing we're going to add is not just the thing that's a little more interesting, but this is really the heart of the interpreter. This is the heart of a scheme interpreter or an interpreter for a language that handles functional programming and is some implementation of a version of the lambda calculus. And so lambda calculus is this theoretical language or a mathematical language invented by Alonzo Church, and it has these 3 expressions: variable lookup, not in the Church style, but sort of in our schemely style, and then it has some expression. These are the lambda calculus expressions, lambda calculus, or lambda calculus terms. I mean, if we really wanted to be formal about this, I would write it a little bit differently, but we're not going to worry about that so much because we're not really implementing lambda calculus. Lambda calculus works a little bit differently than what we're doing. We're doing a call by value lambda calculus, using environments, not using beta reduction or capture avoiding substitution or things like that. These are topics that we might talk about later, but it doesn't really matter. What matters right now is you get some sense of the types of expressions that we're going to deal with. So we have these lambda expressions because we've been using them in scheme. Lambda expression is also called abstraction. It allows you to abstract over computation. And then we have some expression applied to another expression. And then this is what's called application. Okay, so we already know this. We have variables, lambdas, and applications. None of this is new. We already know all this. We're going to add these 3 types of expressions to our interpreter. And once we have those 3 types of expressions, we will be able to handle basically all of computation. We'll be able to handle any computable function, and basically we'll have something equivalent to a Turing machine, at least in theory. Now, in practice, we don't just want to program with those three expressions. It gets awkward. It's useful to have numbers. It's useful to have addition built in, those sorts of things. It's useful to have if built in. But it turns out that you actually don't need any of those things. If all you had was the lambda calculus, that would be sufficient to do to encode a Turing machine, or to do these, to basically do any form of computation where you have an input and then an output. So this is a very, very general way to express computation. And everything else we're doing right now is actually irrelevant. We could just get by with these three clauses, but it's a little hard to see how it works with real example programs. So we've added sort of the calculator part to the interpreter, so we can actually try running some real numeric computations and seeing it work in practice. But just keep in mind that from now on, the lines of the interpreter we really care about are these three lines, and everything else in some sense is irrelevant, because there are ways you can encode numbers, there are ways you can encode conditionals or ifs, things like that, in the lambda calculus, using lambdas, using applications and variables and so forth. Okay, and maybe we'll talk about that at some point. But that's where the point isn't to show you how to do all those things right now. The point is that these are the three language forms we really care about. Okay, and everything else is less important. So we know we're going to have to add variables. Variable, and we're going to have to add application, and we're going to have to have lambda. So we have lambda. Okay, our abstraction, and we have application. Okay, so let's go ahead and add a clause for variables, let's say. So what is that going to look like? Well, our pattern is very simple. We match against anything, and we have a guard. And we're going to, just like we did with environments, represent our variables as symbols. And once again, just like I was talking about with our representation of environments as tag lists or procedures or association lists, it's important to keep in mind that just because we're representing variables as symbols doesn't mean that variables are symbols or symbols are variables or anything like that. This is a representation we're using. We could represent variables as strings. We could represent variables as numbers. There's an approach that does exactly that. It represents variables as numbers, called de Bruijn indices. So we should just keep in mind that a variable in the lambda calculus is this abstract mathematical concept or logical concept. We have a representation of that. Why is it important to keep that in mind? Because over time in different versions of our interpreter, we might want to use different representations. And it's important to keep our mind limber, as the dude might say in The Big Lebowski, right? So we have to avoid sort of over specializing in our mind what a variable is and not confuse our current representation of the variable with the idea of a variable. But for right now, we're going to use a symbol. Okay, so here's our variable case. And what do we do when we have a variable? If I want to know the variable of y, the value of y, what do I do? Well, we already know. We just spent a while doing the lookup. What we have to do is we have to look up the value of the variable in the current environment. So we're going to look up, using one of our lookup functions, the current variable x in the current environment. Okay, fine. Simple. We've already spent a lot of time talking about this. Now, first of all, we have to pick some version of lookup to use and some representation of the environment. We could pick whatever we wanted. Well, let's use an association list though for right now. I don't know, we have 3 different versions of the association list code. I'll use, I don't know, the car cutter one just for fun. We could use any of them though, it would work just fine. So I'm going to add that above the hashbang EOF to make sure that we have a working version of lookup in or for our val expert to call. So now we've got the lookup, but we don't have inv. Inv is not there. One second. So what we need is an environment. Where do we have the environment? Our environment variable is not bound. Well, the only way for it really to make sense is if we pass the environment in. So what we're going to be writing is what's called an environment passing interpreter. It's an interpreter where you pass an environment around everywhere. So what that means is that every single time we have a recursive call to a val expert, we have to make sure we pass in the environment. So here we have to have an environment. Here we have to have an environment. We have to kind of go through and retrofit our interpreter to make sure our recursive calls pass this environment through. Here, here, same here. Okay. So now we're making sure that at any point in the program, we have some environment, and therefore when we have a variable, we can just look up the value in the environment. Easy. And we can actually go ahead and test our interpreter now. So we can test our value, even though we haven't added lambda application, we can test our val expert on variables. So here's a test. So we are going to look up y, remember to quote it, and an environment. And let's say we have an association list where y is bound to 5. Then we should get back 5. Now we have this issue that all of our tests are expecting an eval expert that takes an environment. So we have to be careful and make sure that we start off by giving an environment to our eval experts. You'll notice that we have to put in the quoted empty list. So what we're doing right now is we're leaking our representation of the environment. You can tell from this call to eval expert that we are not using procedures to represent environments. We are not using tagged lists to represent environments. We must be, or at least if we are using tag lists, we have no special tag for the empty environment. We're not using the tag list environment we had below, where we had the symbol of empty env list as our empty environment. So someone looking at this call can tell which representation of the environment we have. And in some ways, that's not very good. We're leaking information. And what this means is that if in the future we wanted to change how we represent the environment and go from association list to a tag list or to a procedure or whatever, we would have to go through and rewrite all of these calls to val expert to change the representation of the empty environment. So we're going to fix that in a minute. But first, let's just make sure that our eval expert actually runs with the, first of all, with all those new environments, and also that we can look up y in an environment where y is bound to 5. So let's just try loading those. Okay, those all pass. Great. Okay, so in the case where we're starting out a computation, if with the empty environment, we probably want to abstract over that at least a little bit. One way we can do that, at least a little bit of abstraction, is by giving a name to the empty environment. So we can just say empty env. We can define a variable named empty env and just make that equal to the empty environment. So now we can replace those, careful with doing it, but those quote empty lists with a reference to empty env. And now you can no longer tell how we're representing that environment. You know, there's that empty end could be bound to a procedure, could be bound to a tag list. You don't actually know how we're representing the environment. Okay, so we've made our code a little more abstract by doing that. Although in this case, you can tell. You can tell that we're using an association list. Okay, so here we're leaking information. We will find ways to abstract over that also. But we'll worry about that a little bit later. The point is, we can now look up the infinite environment. We can now look up a variable. And in order to look up a variable, we have to have an environment. And that means that we have to pass the environment around everywhere. So now we have an environment passing interpreter. It's just that for our calculator, nothing not involving a variable involves this lookup operator. Just to make it clear, we can use the arithmetic operations and our variables at the same time. So we could have add 1 of y, okay, and that's for our add 1, give it a name. So we can mix the calculator operations with the variable lookup, and now we should get 6. Make sure that works. Sure enough, it does. Okay. All right, so that's one of the 3 operators that we care about with our interpreter. Now let's look at the other 2. So we have lambda and we have application. Well, let's handle lambda first. Lambda, the pattern is going to look something like this. Body of lambda and this variable x match against. And if we really wanted to be precise about it or program defensively, we could check to make sure it is indeed a symbol. That we have some symbol here representing the variable. All right, so if that passes, then what are we going to return? Well, what does lambda return in scheme? So if we're looking at scheme, if I type lambda, I get back a procedure. So some representation of procedure, and then that procedure, if I apply it to a value later, then it performs some action. Okay, so that's what we're going to do. We're going to create some representation of a procedure. And, well, how are we going to represent a procedure? Well, there are various ways we can do it, just like there are various ways to represent an environment. Yeah, lambda abides. So how about a tag list? That's right. That's exactly right. We are going to use a tag list. So I could construct a list using list and give it a tag like procedure, and then put any of the information I need inside of it. It turns out that we're going to need some information to apply the procedure. We're going to need to know the name of the variable that's being bound, x, and we're going to need to know the body expression. We can create a list that has a procedure tag that contains that information, and we're also going to have to pass around the current environment. Those are the 3 pieces of information we have to have. Now, to try to keep my code concise, to try to keep my patterns and the lists I'm building up looking as similar as possible, what I'm going to do is, instead of calling lists and quote procedure stuff like that, I'm going to use a tag list using quasi-quote and commas. So procedure x body env. It turns out that when you represent a procedure in this way, the normal way to refer to this representation is as a closure. So instead of using the procedure tag, normally I will use the closure tag. Okay, this is a closure. The reason we call it a closure is that we're closing over the environment. We're remembering the environment in which the lambda expression was evaluated, so that we can use that environment when we actually apply the procedure. This is very, very important. This is where we get our lexical scope, as we'll see later. And if we don't remember the environment, then we don't get our lexical scope, and the scheme scoping won't work properly. So we're going to create a closure. So it's just a tag list. We have the tag list. So if we see a list that begins with the symbol closure and has three items in it, then that's going to tell us, all right, this is a closure. This is a representation of a procedure. Tag list representing a procedure. Okay, and that's all we have. We just return the closure. So that's very simple. Notice we're not evaluating the body. We're not doing anything with the body, and we're not looking up X either. We're not looking up X, and we're not evaluating the body because we don't actually know which value bound is X, what value X is bound to yet. If we apply the procedure or the closure to 5, let's say, in that case, then X will become bound to 5 in an extended environment, and then we can evaluate body in that environment. But we can't evaluate body right now because we don't know the full environment in which body is evaluated with, going to be evaluated. If body has a reference to X, I mean, if our procedure is lambda xx, the identity function, then body is the variable X, and we don't know what X is bound to until we actually apply the procedure. So that's why we can't evaluate body yet. And if that's a little bit confusing, we'll have to trace through some examples, and then hopefully I'll make it more clear. It takes a while to sort of see how all the pieces like interrelate. Okay, but these 3 lines are going to interrelate in important and somewhat subtle ways. All right, it's time for our last operation, our last form, and that's going to be our application line. Okay, so I'll just go ahead and put some reminders here. This is the variable. This is the lambda or abstraction. And now we're going to do the application line. And we are always going to put application last, at least while we're in scheme. When we go to miniKanren, it's going to be a little bit different. But we are going to have some expression E1 applied to some expression E2. That's what it looks like. And by convention, what you often see is that these expressions are called operator and operand. Operator would be like plus, and the operand would be like 5 or something like that. Of course, if we added plus, we might add a special case for it. But the operator could be some procedure created with some lambda, and the operands or whatever arguments will be passed to that procedure. Okay, so operator and operand are standard names, and in at least some books and some papers, they're shortened to rater and rand. Just remember, this is short for operator and operand. Those are the 2 sub-expressions in the procedure application. So, if we're applying some procedure, we got from a lambda to 5, then the operator would be that procedure. Actually, the operator expression would be the lambda expression, and the value of the operator expression would be the procedure. And rand could be plus 2, 3. That's an expression. You evaluate that, and you get 5. Okay, so these are expressions. It's important to remember those are expressions. So what do we have to do? Well, this case is very similar to something like plus, where we have 2 sub-expressions. So we're going to have to evaluate both rater and rand. So far, it just looks like plus. Evaluate the rater expression in the current environment. And we're going to evaluate and now we have to somehow do something with those 2 arguments. Here we called plus. Well, what do we do in scheme? Well, we're trying to do a procedure application. How do you do a procedure application in scheme? You just wrap arguments. So that's it. Application and scheme. Those parentheses mean procedure applications. If you don't really understand the parentheses in scheme, and that parentheses mean a procedure application unless you have a special form, then you'll kind of miss what's going on here. But we're actually applying the value of this call to eval expert. This is better evaluate to an expression. So actually, hold on, sorry, I take it back. I was thinking in my head we were representing expression procedures as procedures, but we're not. We're representing as lists. The talk I gave last week, I was able to write it that way. Okay, so what we do here, this operation, actually it depends on a representation of procedures or closures. Okay, so if we're representing procedures as scheme procedures, then all we have to do is have the parens, and then this will work just fine. Our lambda line has to change, but our application line is simple. But sorry, I got confused for a second because I was using the other approach the other day. But we're not representing the procedures as scheme procedures. So therefore, we can't just do a procedure application because we're going to get back some representation of a closure, which is this tag list. So we're going to get back like the list closure, you know, with some x body and end. And then we're going to get back here, you know, maybe some value like 5. We're going to apply to the closure. So what we really need to do is have some sort of helper that's going to apply that procedure, or apply that closure that we get back from evaluating the operator to the value we get back from expression from evaluating the operand. So that's what we're going to do. We're going to call some helper called apply proc or apply procedure. Okay, so let's define apply proc. We will look at these other variants, by the way. We will represent a procedure as a scheme procedure. We will represent an environment as a scheme procedure. We'll mix and match them a little bit, just so we really have a good sense of the different representations we can use, and play with the interpreter a little bit. It's going to give us a much better sense of kind of how everything connects. In that talk I gave at Papers We Love, I represented both environments and procedures as scheme procedures. It was a very different representation. Okay, so what does apply proc going to look like? Well, we can see that it's going to take some procedure. The value of this operator is going to be a procedure. So we're going to take some proc, and we're going to have some value of some operand. So sort of the example to think in mind would be something like, you know, if we had an expression like lambda xx applied to add 1 of 5, the lambda xx would be, that expression would be a rater. Lambda xx expression is a rater, and the add 1 5 expression is our rand or operand. And what's going to happen is when we evaluate the lambda xx, that is going to turn into something that's going to look like closure. I'll make it lambda yy to make it a little easier to see. Or how about lambda y? I'll do lambda y times yy. That's more interesting. We will get back a closure, you know, because remember we have this pattern matching against the lambda, and it gives us closure back. We're going to have closure with the symbol y, and our body is going to be body of the lambda. So that will be the value of the rater. Okay. And then the value of the rand will just be whatever happens if we evaluate in eval expert, add 1 of 5. And so that's just going to give us 6. So now this is the value of the rater. This is the value of the rand. Oh yes, good call. I need an empty environment, and so I need some sort of environment in the closure. Thank you. Yep, can't forget my environment. That's really important. In this case, the environment's empty, but you know there are other cases where it'll matter a lot. Okay, and so then when we're calling apply proc, proc here is going to be the value of the rater. And so that's the same thing as proc in apply proc. And val is going to be the value of the rand, which is the same thing as val. So in this case, we'd be having this closure y times yy with the empty environment would be your proc, and then val would be 6. So let's keep those in mind as we write this code. So what are we going to do? we're going to use our friend pmatch again. Let's see, pmatch is very helpful. So we're going to pmatch against the procedure or the closure that's passed in. And we know what a closure looks like. We know because we created one up here. So a closure looks like this pattern. I literally can just copy and paste that pattern. We know a closure has some variable x, has some body, and some environment. And now what's going to happen? Well, we want to evaluate the body expression in an environment, which was passed in, this end, extended with a binding between x and val. Val is the thing passed in. So in other words, we're basically evaluating the body of the closure, which would be times yy in this case. We're going to multiply y by itself. But in order to do that, in order to evaluate that expression, we have to know that what y is bound to. So we're going to take the old environment saved in the closure, which in this case is the empty environment, and we're going to extend that empty environment with a binding between y and 6. 6 is our val that got passed in. Y is the variable, the formal parameter in the closure. Okay, so we're just going to extend the environment we had in the closure with an association between y and 6, and that will be the environment in which we use to evaluate the body times yy. And if you evaluate times yy in this environment, it's pretty clear what has to happen. You know, we're doing multiplication. We evaluate the sub-expressions. Y evaluates the 6. Y evaluates the 6. We're just going to multiply 6 by 6 and get 36. So as soon as we can extend the environment because we know what the value of the argument of the procedure is, then we can evaluate the body. We just can't do it any earlier. So we are going to eval for the body, and we have to have an environment. So we are going to build up an environment based on the environment in the closure, where we're just going to cons on another cons pair between x and val. This is our extended environment. I could write this. Looks a little closer to how we were writing everything. If I write this with back quotes and commas, this is what our extended environment looks like. So I'm building up this list where now we have an association between x and the value coming into the procedure. And you know, if we're looking up anything other than x, then we look it up in the old environment. That's all this environment's saying. Okay, so that is our apply proc. All right, and so I'll keep this example around. Actually, I'll just go ahead and write a test for it. So really, I should have a couple tests. So I should have a lambda test. So let me do like, I said lambda y times yy. And I'll do this in a non-empty environment just so we can see what's happening. I'll say z is 17 or something. Okay, what should happen? We should get back a closure. Okay, so we should get back a closure. And here the empty environment. Instead of the empty environment, you know, we just close it was already in place when we evaluated the lambda expression. So we have z being bound to 17. That's what the closure should be. Okay, and now let's try doing our application. Application line. I have a few of these for sure. We're going to apply that to the value of, what do we say, add 1, 5. Okay. Apply that to the value of add 1, 5. And we said that should be 36. And we'll add a few more application tests because application is where it starts getting interesting. But anyway, that this out for right now. So let's see if it runs. And yes, these all run. There was a whole lot going on there. So if you got lost in some of the details, that's okay. We're going to go through it multiple times. This really is the tricky part. The interaction between variables, lambda, and application is the interesting part of this interpreter, and it's very subtle. And it took me, seeing it and thinking through and tracing examples quite a few times before I really started getting the connections. So we're going to do this quite a few times to make sure you really understand what's going on. But we have gotten to the point now where we can write these sorts of programs. So I am going to write one more example just to make sure things are working for the application case, where in this case, actually, I'll do an expression like this. Let me go back up here and kind of work it through. We want to have an expression or an example that really shows what happens with the environment. So let's say we had y, and then let's say we had z or z, and now we are multiplying x by z. Okay, so that's a nice lambda expression, and we can apply that lambda expression. So we have a nested lambda expression basically, and we can apply this thing to, I don't know, add one of 4, and that's going to bind y, be bound to y, the value of that, and then we'll bind to z, do one more application, do like, I don't know, sub 1 of 7. Okay, so what's going to happen is, it's maybe a little hard to read, but this should be equivalent to doing something like, oh, I have x instead of z in multiplication. Yeah, thank you. YC. Okay, so this is going to be like if we said, y is make sure I get it right order. Let's actually, this is the opposite, right? So oh yeah, I'm not doing direct application, so I can't turn this in lets. Never mind. Well, what's going to happen? Let's just kind of break this down. This is a little. So let's look at sort of the innermost application. So we have 2 procedure applications. So the innermost application is we're applying this lambda y, lambda z times yz thing to add 1 of 4. Well, we know add 1 of 4 is going to evaluate to 5. Okay. So it's the same as if we applied this to 5. So what's going to happen is, basically when we do the application, this lambda expression will turn into a closure. Right, so the lambda expression itself will turn into a closure, and so this will be a closure. Its variable is y, and whose body is lambda z times yz, and this will be in the empty environment. Okay, and we said add 1 4. I mean, I guess I'll try to be a little methodical here. We know add 1 4 is going to evaluate to 5. Okay, so that's how our evaluation is going to work. So now we're going to do a procedure application, and now we're going to basically do an apply proc on that closure. This is going to be our proc value, and our val is going to be 5. So that means we're going to apply, or sorry, evaluate the body of the closure, which is this lambda expression, in an extended environment where y is bound to 5. Okay, so that's what happens with the innermost application. And here we'll get back a closure. This lambda expression itself will evaluate to a closure. in this environment, in the current environment. And this closure is what is going to be applied to, as part of our outer application, the sub1z thing. Sub1z is going to evaluate to 6. Basically, we're going to have another application, another apply proc, where the proc is this, and the val is this. And once again, now we're going to go through our steps, and we're going to evaluate of the closure, which is this. Take the old environment of the closure, and we're going to extend that environment with a binding between the formal parameter of the closure, z, and the value, which is 6. So now we're multiplying y times z in this environment. Okay, so when we do the multiplication, we have to evaluate the sub-expressions. Y is going to be 5, z is going to be 6, and we should get 30 if I did my calculation right. So let's just try this example. So I wanted to make sure I had an example where I had nested lambdas, basically, in multiple applications to really make sure that I was handling the environment correctly. You'll find once you start writing these interpreters, if you always has to do with the environment, or otherwise has to do with lambda application or the variable case. Everything else is usually pretty straightforward, or if you do make an error, it's like a pretty shallow error that's immediately obvious. But it's once you get involved with the environment where it gets a little tricky. So here's our second case. And we're going to evaluate this in the empty environment. And what did I say? It's 6 times 5 is 30, right? So just to be fun, I'm going to put 29. So that should fail. I just want to see that we are actually testing it properly. Yeah, expected 29, but got 30. That's perfect. Okay, good. Testing technology is running, and all of our tests run. Okay. So that shows that we are getting our lexical scope right. And we could do more complicated examples. I mean, it doesn't really show anything, right? I mean, no, the testing isn't going to prove anything, but that's some evidence that we didn't screw it up completely. So we will add some more tests, but we're going to add one more test right now that will show sort of why we added the rest of this calculator part. We're actually going to do an arithmetic calculation. So I didn't realize the mutually dependent functions do not have to be explicitly declared in scheme. That's right. So you don't have to declare those functions to be mutually dependent. So if val expr and apply proc actually call each other, but they do not have to be defined in some special way. Scheme will handle that. Yes, in closure you have to use declare. That's right. If you're doing this in closure, you'd have to use declare. In scheme, you don't have to do that. It's a good point. Okay, so let's just try one fun example, and I'll just bring it up, and I think that will be so. That'll sort of close it out for today, and then next time we can dive into the interpreter a little more and talk about how it could change the environment representation, how it can change the procedure representation, trace through a few more examples, play around with lexical versus dynamic scope, and just try to get a better feel for the interpreter. I mean, this is an awful lot to see at once. I think it'll take a few times to really wrap your head around it. If you haven't seen it before, that's okay. One thing that Dan Friedman suggests is is just trying to write down the interpreter a few times yourself. And next time we will see a different way to write this interpreter with a different representation, procedural representation of environments and procedures. That is very, very short. It fits on like a 3x5 card. It fits on a very small index card. And I'd recommend you try writing it down a few times and thinking it through and tracing through how the interpreter works. So, I spent 45 minutes, just writing that interpreter down over and over again many times before I kind of had it seared. So actually, I know I have this code in the papers we love. Yeah. All right. Here we go. Here we go. This is what I was looking for. So there's one thing that our interpreter doesn't seem to have that seems to be very, very important if you've thought about what we've done in the past. If we want to define any interesting procedure, function, and scheme, you've noticed that they're all recursive. Everything interesting that we've done is recursive, where we have a procedure that can call itself. And we don't seem to have any way of having a procedure call itself. We have lambda and we have application, but we don't have define. There's no way to give a name to a lambda using define. We don't have letrec, which allows you to define mutually recursive functions. So how in the world would we ever write a recursive function? Like, say, for example, we want to define factorial. Factorial, some number, just factorial 5 is 5 times 4 times 3 times 2 times 1, that sort of thing. So what if we wanted to do something factorial, work on any integer that's positive? We don't know how big the integer is. We don't know how many multiplications we have to do. We need recursion. So it seems like we're stuck unless we add define, unless we add letrec. And we could do that. We could add define or letrec to our interpreter. And in fact, the Barlaman interpreter does that. And we'll see how to add that. But right now, we're a little bit stuck. So it turns out that there's this really amazing result that once you have the lambda calculus, once you have lambda and application and variables, you don't actually need define, you don't need letrec to do things in a recursive way. Instead, there's a special lambda expression you can write called the Y combinator that you can use to give yourself the ability of writing recursive procedures. And in Scheme, which is a call by value language, and we'll learn later what that means, instead of the Y combinator, use the Z combinator. It's slightly different, but it's the same sort of idea. And at some point we might get into that a little bit and talk about those combinators, what that means. Very, very interesting. It's a whole theory of combinators, and that's also fun to explore with relational programming and functional programming. But for right now, we're going to punt on that issue. And I'm not really going to explain kind of how this works. I'm just going to say that it does, and I'll show it to you working in Scheme. We can use what Dan Friedman calls the poor man's Y combinator, which is a similar in spirit, but it's not really the Y combinator. It's sort of inspired by the Y combinator, if you will. And I'll just, this thing works. But before I show you, really get into that, I'll just let me just define factorial the normal way. So in Scheme, we have factorial or fact, and we tend to use the exclamation point, maybe just to show off in Scheme that we can use that as an identifier. But basically, factorial is going to take a number, and we're going to check to see if that number is 0. And if it is, then we just return 1. Otherwise, we are going to multiply by n, the recursive call, on one line. So if you factor 5, that gives me 120. Factor 6 gives me 720, that sort of thing. So factor 5 is 5 times 4 times 3 times 2 times 1. And we're just doing a chain of multiplications. So this is the standard way of writing factorial using define. If I use letrec and scheme, okay, if I use scheme, letrec works similarly. I could give the name factorial and associate with that name, just like I associate something with let, a name value of this lambda expression. And then within the body letrec, I can call factorial of 5. Okay, and let and letrec differ in that let allows me to bind a variable to a procedure. That's fine, but the procedure, because of the scoping rules of let, that procedure cannot refer to itself, because in a let, the right-hand side does not see the left-hand side variables. So this factorial thing, this bang, is not associated in any way with this bang on the left inside of a let expression. Except I already defined bang, so it worked accidentally, but it worked because this exclamation point thing was already defined. If I define exclamation point to be, car, then the function breaks. Car, error in car, 4 is not a pair. Whereas if I go to letrec will still work even though I redefined exclamation point at the top level, because this exclamation point here refers to the exclamation point being defined on the left-hand side. So that's the difference between let and letrec. And we'll implement letrec at some point, and that will make it even more clear. But anyway, they have different scoping rules. So one way you can define factorial is using define. Another way is using letrec. And then, another way to perform factorial is using this kind of weird operation where we have something that looks kind of like factorial. You can see factorial sort of hiding inside of here, right? So you can see the operations. We've got a lambda in and an if and a 1 and a multiplication and recursion and all that stuff. So that looks very similar to what we have in terms of our definitions, with one difference. We've, instead of making the recursive call directly by a single variable lookup to exclamation point, now we have this additional application. We have factorial applied to factorial. It's kind of interesting. And outside the lambda in is another lambda that has, as this argument, the name factorial. So letrec lets you bind this variable, the exclamation point, to something, but lambda also lets you bind things. So basically what we're doing is we're using a trick. We're using the fact that lambda can introduce variables so that we can do a similar operation just using lambda instead of having to use letrec or define. And it turns out that we have to be a little careful and play this kind of game where we have this the lambda, the exclamation point being applied to itself in a couple places. We can derive how this code works and why it works, but the key point is that we don't actually need define. We don't need letrec in our language to actually use recursion, which is actually a really remarkable result. And there are various ways to do it in terms of combinators, and this poor man's let is one way to do it. But what's important for our purposes right now is it allows us to take this expression and use it to test our eval expr, even though we haven't added letrec or define. We can actually just try this. So we can say test fact 405, and we're going to do eval expr. And we're going to run that in our empty environment. Oh yeah, I should have used empty end down here. That should be a little more abstract. I'll get a quote on 30. Okay. All right. So we should be able to evaluate this expression, assuming we implement everything. We implement lambda, if, 0, question mark, numbers, multiplication, sub 1. Okay, so I think that should work. And we should get 120 back. So let's just try that. Sure enough, it worked. Okay. And one of the things that Dan Freeman always points out is that if you can handle factorial of 5, this tests all sorts of things. Lambda, application, nested lambda, lexical environment, variable lookup. So if you can do all of those things correctly, you probably have, either a correct implementation of your interpreter, or at least the basic parts of it, the application, lambda, and variable lines, or you must be very, very close to it. So it's, if the factorial 5 test passes, you probably have some confidence that you have at least the basic interpreter working. So this is a really good test. Or maybe to put it another way, if this test tends to uncover all sorts of errors, including subtle errors in your interpreter. So always run the factorial 5 test. And furthermore, you don't need define or letrec in order to define in order to run this test. So you can run this pretty early. As soon as you have, lambda, application, variables, if, 0, multiplication, sub 1, numbers, you can run this test. And now we've run the test. If we really wanted to, we could kind of get rid of a whole bunch of these clauses if we didn't care about them. Because, like I said before, we really only need variables, lambdas, and applications. If we just wanted to do something very, very minimal, or just add a few operators to it, it's not really necessary that we have add 1 and sub 1. It's not. We could just use plus instead. We could add plus instead. So at this point, we can start deciding what language forms we want to keep around, or how big we want our interpreter, how big we want the language being interpreted, that kind of thing. But we've got the core parts of a basic environment passing call by value interpreter for a subset of scheme now working. And it's tested, seems like we're working. We also wrote this test macro. So now we've got another example of a syntax rules macro. And we've seen a little bit about how you format output in Scheme. And we've got a bunch of tests running. You can never have enough tests. And if you notice, I was quite careful to make sure every time I tested something in the REPL, I added a test for that in the file, so that as we build on the interpreter or change the interpreter, we'll always be able to run our tests and make sure we still get the same answer. Okay, so that was a lot of ground that we've covered in 2.5 hours or whatever. And I think this is a good place to stop. Like I said several times, don't be surprised if you haven't seen this before, if some of these aspects still seem confusing or missing detail, or it's just a lot to take in, or you're still confused about the connection between the different forms, especially the lambda, application, and variable lines of the interpreter, or if this poor man's Y Combinator looks confusing, or if letrec's still a little confusing to you. We'll fill in the details, and as we go, you'll become more and more comfortable with it. And hopefully you'll have lots of questions as we go as well. But at some point we'll add letrec to the interpreter. At some point we will, talk about combinators and look at how you would derive one of these combinators, or how we can derive the code for that version of factorial, that kind of thing. And we'll trace through a bunch of examples with the interpreter, and we'll look at how we could represent environments in different ways as procedures, and how we can represent procedures or closures as scheme procedures. And we'll look at a very different looking version of the interpreter that still works, but when we represent environments and procedures using scheme procedures, the interpreter is very, very small. We don't have to have these helper functions of apply, proc, and lookup. It's very small and it's very abstract, and it's actually the version of the interpreter I prefer to think about, but it's also much harder to trace through the interpreter, and it's a little harder, I think, maybe to wrap your head around when you're first getting started, but you should really understand both of those versions. And we'll talk about that plenty coming up too. Okay, let's see, some questions here. Isn't that what Y is for? Yes. Yes, you were ahead, Daniel. Naming things is literally hard here. Yes, the naming thing is hard, except lambda, right? Lambda is our giant hammer. The unifications are giant hammer when we get to logic programming. Lambdas are giant hammer in functional programming. Mind begins imploding, yes. Can you invent if with just variable subtraction application? Yes, you can. Yes, you can. Yeah, yes, you can. So one place I'll point you to. Well, let me just double check real quick here. I know Matt Might has on his blog things about church encoding, lambda calculus, I think. Yeah. So yeah, let me look at some of these resources, and I will. I'll post some of these that I think are probably clear. So I know Matt might have some good blog posts related to church encoding of numbers, and I think he also talks about the conditionals, like how you encode true and false as a lambda, because you can do that, and that sort of gives you if-ish behavior. And also, how do you derive these combinators that you use so you don't need recursion? There's this whole art, this whole beautiful area. You can do subtraction and addition and things like that using lambda, and encode numbers using lambda. It's really remarkable. It's really fun to look at that also. Let's see, it kind of flew over my head. Is our lambda using closure one level down, or are we relying directly on schemes lambda? We're not relying directly on schemes lambda in this version. We're representing our closures as tagged lists. That's where I get confused for a second, because a couple days ago I was showing people how to represent closures as scheme procedures, using schemes lambda to represent lambda in our interpreter, and you can do that, and it's really elegant. It's beautiful, and so we'll look at that next time. It's a different feel. It feels a little more abstract, but it's very concise, and I think it's really beautiful. And that's what I gave the talk at the Papers We Love. The interpreter I showed used schemes lambda to represent environment and used schemes lambda to represent closures. And so I had a totally different kind of buildup. Which way is better? I think it's different trade-offs. For people who've seen functional programming before and are comfortable with it, I think seeing the lambda version of everything is probably the way to go to start. For people who maybe are newer to programming and they're still learning pattern matching and lists and lambda and lexical scope and all these things, my current thinking is that showing them the lambda version of everything up front is maybe a little too much, but I don't know. Maybe we're going to look at both, okay? And really, you want to understand both versions of it, and you can actually mix these. You can have the procedures, scheme procedures represented, or procedures in our language represented as scheme procedures, but environments represented as tagged lists or association lists, or you can have environments represented as scheme procedures, and procedures or closures represented as tag lists. You can mix and match these things, and those are some of the games that we'll probably play with a little bit, just to make sure we're comfortable with that. If you take Dan's class C311 or his graduate class 521, they spend weeks and weeks doing all this stuff. So we're going through this really quickly, but we're hitting the main points, and we can always dive into some of the details more. I mean, you can make a career studying these sorts of things. They're quite deep. And some of the topics, like the combinators, that stuff's super deep. They're mathematicians and logicians who spend all the time studying combinators. So. And it turns out that there are ways in miniKanren to do things just like Barlaman can generate scheme programs. You can also do things like generate combinators, like the Y combinator. You can do things like that in miniKanren if you write a combinator reducer in miniKanren. So maybe we'll take a look at that at some point. That one's a little frustrating for me because I haven't figured out how to make that run very fast. We've made a lot of progress with making our scheme interpreters run fast in miniKanren when doing program synthesis. Or, I mean, maybe fast isn't the right word, but far less slow. Sped up many orders of magnitude, but I haven't figured out how to speed up the combinator reducer in miniKanren. So maybe people have ideas for that. So anyway, we went through a whole lot today. I don't expect anyone to wrap their head around it if they haven't seen this stuff before, to wrap around everything. But I do encourage you to think about it and maybe rewatch the video and just make sure that you start understanding, especially those three lines, the application, environment, application, variable, and lambda lines, right? Those are the key lines of the interpreter. If you understand those lines, the rest of it isn't so important. Those are just following a simple pattern. But you have to understand those three lines and how they interact. And one of the things we'll do next time is talk in more detail about the connections between those three lines, and I'll draw some parallels and try to point out, this argument corresponds to the value of this expression and things like that. And once you've seen that a few times, I think it helps you out. And if you just trace through some of these examples and see what the closures look like, and what the environment looks like, inside the closure and stuff like that. So this is something where tracing through the evaluation of the program will help a lot. And I'll post the code for this. I definitely recommend that you try playing around with the evaluator and trying to predict what the closures would look like for certain lambdas, or try tracing it through by hand or whatever. Okay, this is the time where you really need to start playing around with it. And any time you spend now understanding this interpreter will pay off huge dividends. Anything else you do having to do with interpreters or things like that in the future, not just from the standpoint of what we're doing with miniKanren or whatever, but just in general. You'll understand programming languages much better. You'll understand scoping of variables much better. You'll understand how letrec works and things like that once we start adding that. Everything's connected to this environment. You really have to understand how that works. That's the key. Okay. Any last questions before I stop the broadcast? I'll hang out for a few minutes afterwards. People want to talk. Okay, I don't hear any questions right now. So yeah, I'll post the code once the video comes up, and then actually I'll post the code now, and I encourage you to play with it. And then next time we can, next Saturday we can look at the higher order version of the interpreter using lambdas everywhere, and that's really small. It's really beautiful, really elegant. That's basically what I gave a talk at Papers We Love. The name of my talk was The Most Beautiful Program Ever Written. And I was talking about that interpreter written using lambdas. And I'm completely serious. I think that's the most beautiful program that's ever been written. We haven't seen it yet. I've shown you kind of the ugly version of it. but we're going to see the beautiful version of it next, and hopefully, come to grow to appreciate and love it as much as I have. Okay, so that's next week, the most beautiful program ever written. Until then, later.